Hey, it's Mr. Shrum, and I am back again with a tutorial walkthrough for physical science. And we are looking at magnets today and their fields. So we're going to explore some basic properties of magnets, including their interactions, field lines, and relationship to electricity, because electromagnetism is a dynamic between electricity and magnetism. Getting into our intro, mid-1800s, oil lamps and candles provided most of the lighting. Ice boxes kept our food cold. Wood or coal-burning stoves provided heat for us when it was cooler weather. Those everyday methods changed when electricity became available to homes and businesses. And that innovation provided the fuel that powered the second half of the Industrial Revolution. And one of the most important contributors to the development of commercial electricity was a very smart, very experimental scientist named Nikola Tesla. He was an engineer, physicist, polyglot. He spoke a lot of languages. And he's best known for his innovations in the field of electromagnetism. They named an SI unit after him, and he's been recognized by a lot of societies. So Inventors Hall of Fame, he was commemorated with a US postal stamp, and there are several statues of him places. So he's recognized as an important figure in the science community. There was a famous fight between Tesla and Thomas Edison. Edison, let's say, he's a very interesting cutthroat character. He was a supporter of DC current, which means direct current electricity, while Nikola Tesla thought alternating current, AC electricity, was much more efficient. And over time, Tesla's idea proved to be much better in the long run. And he was also really interested in the phenomenon of magnetism. He understood that electricity and magnetism were two sides of the same coin, and that coin being electromagnetism. Electromagnetism is one of the four basic forces in the universe. To harness the full potential of electricity, you need to understand magnetism as well. So in this lesson, we're going to learn about the basics of magnetism and magnetic fields. So here we go. We use magnets every day to hold pictures and calendars onto our refrigerators. But do you ever wonder how they work? The word magnetism is derived from magnesia. This is a region of Greece where unique rocks called lodestones were discovered more than 2,000 years ago. These stones attract iron pieces and were used by the Chinese in the 12th century to make the first compasses. Magnetism is the force of attraction and repulsion in and around a magnetized object. Charged particles within the atoms of these objects are moving. Any moving electrical charge will create a magnetic field as long as it is not counterbalanced by charges moving in the opposite direction. Metals like iron, cobalt, and nickel exhibit magnetic properties due to their atomic structures. You can also create a magnetic field by running a current through a wire. Like electrical forces, the magnetic forces in a magnetic metal can both attract and repel objects over a distance. without physical contact. The magnetic forces around a magnet are not uniform. There is strong concentration of forces at each end of the magnet, and it weakens at the center. So if you look at this diagram, we have iron filings on the ends of a horseshoe magnet. Look how they're more concentrated towards the ends, and then not concentrated in the middle of that horseshoe. So look at all the black concentration and the lack of black concentration here. The two ends of a magnet are called magnetic poles. All magnets have two poles that are equal in magnetic strength. When a magnet is suspended on a string, it will align itself with the north and south poles of Earth. And if you kept looking at it, you would notice that the same end of the magnet always moves towards the same direction. It has a north-seeking pole and a south-seeking pole, or North Pole and South Pole. That's just the basic names for it. So we'll keep North Pole and South Pole. It's easier to understand. When two magnets come into contact with each other, the rule of attraction and repulsion is simple. Like poles repel, opposite poles attract. And how powerful they are depends on how close they are to each other. Magnets can be either permanent or temporary. Once magnetized, a permanent magnet will retain its magnetic property. Permanent magnets are called ferromagnetic magnets. Ferrum is the Latin word for iron, and a good example is a refrigerator magnet. Temporary magnets, in contrast, can be magnetized, but they then lose this property when the magnetic source is taken away. Examples include paper clips, nails, and other objects containing soft iron. We know that an electric field surrounds an electric charge. A magnet is similarly surrounded by a magnetic field. These fields are vector quantities and can be felt when one permanent magnet exerts a force on another and the two magnetic fields interact. If you look at planet Earth, it acts like a permanent magnet. We know the north pole of a compass needle points north. The magnetic pole of Earth that is located geographically north is magnetically a south pole. This fact follows from the rule that north and south poles attract each other. Therefore, Earth's magnetic poles do not match the planet's geographic poles, which are on Earth's axis of rotation. So look at this. A little different. Checkpoint question: which statement about magnets is true? If a magnet repels an object, the object is also a magnet. That indicates they're magnets. So attraction or repel. When you think of magnets, you might think of a compass. Compasses have been used for centuries as navigation tools, and the north-seeking pole of a compass needle always points within a few degrees of due north. Knowing which direction is north has enabled explorers to circumnavigate the globe, and it lets lost hikers find their way out of dense forests. This video shows how compasses work with magnetic fields and even demonstrates how to make a simple compass with a cork and a sewing needle. You'll see magnetic field lines indicated by iron filings, magnetized needles, and small magnets. Each of these illustrations helps to explain what happens in a magnetic field. This explains the Earth as a magnet. And then we have the compass. And if you look at the compasses, they all point towards the pole, and in different ways. But you see these lines, they're very curved. So that is magnetizing a sewing needle. They stick it through a cork, they put it in water, and then they set a magnet. And the sewing needle always goes towards one end of the magnet. And you see how it moves in a very curved way, depending on where you put it. Okay, this is a cool example. Turn off the sound. So they sprinkle these iron filings onto the magnet, and you see how they concentrate and they're pulled towards the pole. But they also stick it in this tube, and the tube is filled with iron filings. And you can see how they curve around the poles. And they form these really cool looking field lines. We use magnets every day: televisions, electric motors, computer hard drives, can openers, and machines that sort coins are just a few devices that use magnets. MRIs, or magnetic resonance imaging, is used in the medical field. This is a diagnostic technique that has two types of magnets. Primary magnets create images with strong magnetic fields. Gradient magnets are the fine detail component of the MRI, and those magnets help focus and create images of specific parts of the body. They are also used in neurosurgery, and they can help a surgeon locate and treat an otherwise inoperable tumor. And that does not damage the surrounding tissue as much. And research continues. All right, so I will stop there for now, and I will pick up when I see you guys again. But until next time, have a good one and stay safe. All right, bye-bye.